Welcome to this deep dive, custom tailored just for you.
Yeah, we have a really, really fascinating one today.
We really do. I mean, our mission today is to explore a truly mind-bending question drawn from your stack of sources on quantum mechanics and, well, the philosophy of reality.
Right, it's a huge topic.
It is. The central question we're trying to answer for you today is, does the universe need a witness?
Exactly.
Like, if a star explodes in a distant galaxy that no mind will ever actually see, did it actually happen? Okay, let's unpack this.
To really get to the bottom of that question,
Yeah.
I think we need to start with the baseline of reality that we all, kind of already agree on.
Right.
Like, we have to establish how we know things exist when we aren't directly looking at them.
Yeah, because most of us are perfectly comfortable saying the moon exists when our backs are turned.
Oh, for sure.
We don't need to be staring at it to know it's up there doing its job, pulling the tides across the oceans, gravitationally anchoring the Earth's tilt. And as one of the sources jokes, keeping the werewolves busy.
Right, the werewolves. But seriously, we verify its existence through its indirect physical effects.
Exactly.
And the same logic applies to local stars in our own galactic neighborhood.
Like the ones we can actually see in the night sky.
Yeah, exactly. We don't need a telescope trained on them 24 hours a day to prove they're real.
Right.
Because they reliably exert gravitational influence on their neighbors, they tug on orbiting exoplanets, and they continuously pump out photons that eventually hit our detectors.
So we see the constant, ongoing evidence of their physical labor in the universe.
Exactly.
But the real puzzle begins when we stretch that logic to its absolute limit.
Yeah, this is where it gets weird.
Right. What about a star in a distant dwarf galaxy, like unimaginably far away?
We're talking about a star so isolated that we will never observe it.
Never. No telescope we ever build will capture its light.
No.
We will never detect its gravitational pull, and no signal from it will ever reach our solar system. So does that star actually exist right now? Or is it, in the language of quantum mechanics, just pure potential?
Like a fuzzy quantum probability cloud.
Exactly. A probability cloud waiting for a sentient mind to finally interact with it and collapse it into a definite reality.
Framing the problem as a probability cloud waiting to collapse is a very quantum mechanical approach.
Yeah.
And it's actually a completely valid, deeply debated question in fundamental physics.
Okay.
But to answer it, we first need to define what the word observe actually means in a scientific context.
Which is probably not what I think it means.
Right. The definition usually surprises people who aren't quantum physicists.
I am bracing myself because redefining observation to mean something that doesn't actually involve an observer feels like a massive linguistic cheat.
I get that.
Like if an atom bumps into another atom in the dark void of space and absolutely nobody is there to record it, calling that an observation sounds like, I don't know, playing with words to avoid a serious philosophical headache.
I completely understand why it feels like physicists are just moving the goalposts to avoid the philosophy.
Right.
But the distinction is incredibly precise, and it's mechanically crucial to how the universe actually functions.
Okay, so how do they define it?
Well, in quantum terms, an observation does not require a human eye, a telescope, or a mind.
Wow.
It simply means an interaction. Any physical interaction whatsoever qualifies.
So consciousness is entirely removed from the equation?
Yeah.
Just physical contact does the trick?
Exactly. If a single photon of light strikes a stray, lifeless dust particle floating in deep space, that dust particle has just observed the photon.
Oh, wow.
Yeah. If two hydrogen atoms collide in a vacuum, they are observing each other.
That is wild.
Whenever a fragile quantum system interacts with its surrounding environment, that environment forces the system to pick a definite state.
Okay, so if we apply that definition back to our lonely, unobservable star in that distant dwarf galaxy.
It's being observed constantly.
Right, constantly.
Continuously, actually.
Mm-hmm.
Trillions upon trillions of times, every single fraction of a second.
Because all its parts are interacting.
Exactly. That star is being observed by its own internal nuclear fusion reactions.
Right.
It is being observed by the plasma. It's superheating. It's being observed by the faint gravitational ripples it continuously sends out across the fabric of space-time.
And by every single photon, it violently ejects into the cosmic void.
Exactly.
So those constant interactions are what force the star out of being a blurry mathematical probability and into being a definite physical fiery object.
Physicists call that process decoherence.
Decoherence, okay.
Yeah. It is the exact mechanical process by which quantum fuzziness resolves into classical, solid reality.
Okay, can you give me an analogy for that?
Sure. Think of a pristine quantum state, like a perfectly balanced spinning coin.
Okay.
As long as it is completely isolated, it is both heads and tails simultaneously. It's just a blur of probability.
Right, like an unbroken blur.
But the environment is like a barrage of tennis balls hitting that coin.
Oh, okay. So the spinning coin can't stay perfectly balanced when it's being battered by the environment.
Exactly. The coin gets knocked over immediately. Its delicate quantum state becomes scrambled and entangled with the trillions of other particles in the room.
It's forced to pick heads or tails.
Right. The information about its fuzziness doesn't disappear, it just leaks out into the surrounding environment until it is impossible to measure locally.
Got it.
So, because the distant star is constantly entangled with its chaotic environment, its quantum possibilities leak out instantly.
Meaning the star isn't sitting out there in the dark like a ghost, holding its breath, waiting for a human being with a telescope to finally notice it so it can pop into physical existence.
No, not at all. It is continuously collapsing its own wave function through its own sheer existence and furious physical activity.
Wow.
According to the mainstream physics consensus, that star exists fully, completely, and objectively.
Oh.
The universe is not waiting around for our attention to make things real.
But, if decoherence provides such a clean mechanical answer, why is this still a debate?
Because here's where it gets really interesting. Because some of the greatest minds in history looked at mainstream physics and concluded it was missing a crucial ingredient.
Yes, they did.
And that brings us to the ultimate 20th century polymath, John von Neumann.
Oh, von Neumann. His intellect was so vast, it is genuinely difficult to summarize.
It really is.
His processing speed and his ability to hold complex logical structures in his head were legendary among the smartest people on the planet.
I mean, he practically laid the foundational architecture for modern computing.
Yep.
He invented game theory. He was a critical mathematical engine behind the Manhattan Project.
Absolutely.
There was actually this ongoing half-serious joke among his genius colleagues at Los Alamos during the 1940s.
Oh, I love this story.
They honestly weren't sure if von Neumann was a human being who could somehow compute like a machine, or if he was actually a highly advanced extraterrestrial machine that had learned to flawlessly simulate being human.
Right. He was just that smart. And his contribution to quantum mechanics was just as foundational.
Well, in 1932, he published Mathematical Foundations of Quantum Mechanics.
Okay.
Before von Neumann, quantum theory was undeniably brilliant, but it was a bit of a mathematical patchwork.
Like, kind of messy.
Yeah. Different pioneers were using different mathematical languages to describe the exact same phenomena.
Oh, that sounds confusing.
It was. So von Neumann stepped in and united them, giving the entire field a rigorous, bulletproof mathematical structure known as Hilbert space.
But the truly wild part is what this incredibly rigorous, hyperlogical human computer concluded about the fundamental nature of reality.
Yes. Von Neumann looked deeply at the mathematics of the wave function collapsing. You know, that transition from probability to reality via interaction that we were just discussing.
Right, the decoherence stuff.
Exactly.
Okay.
And he formalized something known as the measurement chain.
Okay.
He realized that tracing the physical interactions creates a massive logical infinite regress.
Wait, walk us through the mechanics of that measurement chain. How does the infinite regress actually happen?
Let's track a laboratory measurement step by step.
Okay, I'm with you.
Imagine a scientific device designed to measure a single quantum particle, like an electron, in a state of probability.
Got it.
The machine interacts with the electron. According to the pure, unbroken mathematics of quantum theory, the machine shouldn't just force the electron to pick a state.
Really?
No. Instead, the machine itself should now enter a state of probability. It becomes entangled with the electron.
So the machine is now existing in a blur of multiple possible readouts at the same time?
Exactly.
The fuzziness basically spreads from the microscopic particle to the macroscopic machine.
Right. Now imagine a scientist looks at the machine's digital display screen.
Okay.
Light travels from the screen to the scientist's eye. The light, the screen, and the particle are all part of a continuous physical chain.
Right, they're all connected.
The light hits the retina. The optic nerve fires electrical signals to the visual cortex in the brain.
Okay.
And all of these components, the eye, the nerve, the brain tissue, are made of atoms. All of them are physical processes dictated by quantum equations.
Oh, I see where this is going. If the brain is just another physical system made of quantum particles, it should just become entangled too.
Exactly.
The scientist's brain is now in a superposition of having seen multiple different results. So where does the decision happen that forces the universe to pick one definite timeline?
That was von Neumann's trap.
Wow.
He proved mathematically that as long as you are tracing physical interactions, particle to sensor, sensor to light, light to eye to brain, there is absolutely nothing in the equations that forces a definitive collapse.
Nothing at all.
Nothing. The math just keeps passing the buck down the physical chain.
Like an infinitely long line of dominoes that lean into each other but never actually fall flat to the floor.
That's a great way to put it.
Yeah.
Von Neumann concluded that the buck cannot stop within the physical universe.
Okay.
You have to push the chain all the way up until you hit something that is fundamentally not governed by physical quantum equations.
And what would that be?
The only thing he could identify that sits completely outside the physical machinery of the universe is the subjective, non-physical experience of consciousness.
So the conscious observer is the only thing that can finally collapse the wave function.
Yes, a philosophical position known as idealism.
Wow.
What's fascinating here is that one of the 20th century's most rigorous, rational, mathematically uncompromising minds was inescapably drawn to a conclusion that sounds almost mystical.
It really does.
He believed that objective physical reality mathematically requires a subjective mind to lock it into place.
But if von Neumann is right, and a conscious mind is the required final link in the chain, then that unobserved star in the distant dwarf galaxy becomes a massive problem again.
It becomes a huge problem.
Because if there's no mind anywhere to finally stop the buck, we really have to grasp exactly how much of the universe is out there completely, utterly unobserved.
The scale of the unobserved universe is genuinely staggering. It literally breaks the human capacity for spatial reasoning.
It totally does. Let's put some hard numbers to it for you. There is a classic comparison that often gets referenced in your sources.
Right, stars versus grains of sand.
Exactly. If you take every single grain of sand on every beach, every desert, and every riverbed on planet Earth,
Which is a lot of sand.
current geological estimates put that number at roughly 7.5 quintillion.
That is 7.5 multiplied by 10 to the power of 18. An incomprehensibly massive pile of tiny individual rocks.
Right. Now we look up at the sky. Current cosmological estimates for just the observable universe suggest there are somewhere between 100 billion and 400 billion individual galaxies out there.
Right.
And each of those galaxies contains an average of 100 billion stars.
So multiplying those figures together yields roughly a septillion stars.
A septillion.
That is 10 to the power of 24.
To picture what a septillion actually looks like in relation to our world, imagine walking on a beach.
Okay.
You bend down and pick up a single microscopic grain of sand on the tip of your finger. For that one tiny speck of dirt, there are 100,000 blazing, massive stars existing in the universe.
Wow.
One grain of sand, 100,000 suns. Every time you take a step on the beach, you are crushing trillions of potential solar systems beneath your heel.
And we must also remember that a septillion is merely the star count for the observable universe.
Right, just the part we can see.
Exactly. It's the localized bubble of the cosmos, whose light has had enough time to reach us since the Big Bang.
Okay.
If the universe is spatially infinite, which many leading cosmologists strongly suspect it is, then the number of unseen, unobserved stars isn't a septillion. It is literally infinite.
So how are we supposed to reconcile this overwhelming, indifferent scale with the philosophical idea that the universe somehow requires a conscious mind to observe it into existence?
It's a tough pill to swallow.
Because it feels incredibly arrogant to look at 100,000 hidden stars per grain of sand and assume their existence is somehow tethered to human awareness.
It sounds absurdly arrogant when framed as humanity being the center of the cosmic project.
Yeah.
The sheer scale of the cosmos forces a paradigm shift. We have to completely stop viewing the universe as a vast, empty warehouse filled with isolated, lonely objects sitting in the dark, waiting to be found.
Well, if the universe isn't a collection of isolated objects, how should we conceptualize it?
If we connect this to the bigger picture, we have to recognize that the universe is an intrinsically woven web.
A web?
Yeah. Gravity and quantum fields don't just exist passively in the universe. They actively connect every single piece of it.
Oh, I see.
Every particle is entangled to some microscopic degree with the quantum fields around it. Gravity propagates infinitely across the void.
So that lonely star in the dwarf galaxy isn't actually isolated at all. It is tugging on the fabric of everything else.
Exactly, because the universe is one vast, deeply entangled, self-interacting system. Asking if a distant star exists when no human is looking is like asking if a single specific neuron in your brain exists when you aren't actively thinking about it.
Well, the neuron obviously exists, but its existence is defined by its participation in the larger neural network. It fires, it interacts, and receives signals from its neighboring cells completely independent of my conscious attention.
The universe operates much the same way. It is acting as one enormous self-observing process.
Wow.
This represents a massive shift from how science viewed reality a few centuries ago.
How so?
The old Newtonian view saw the universe as a giant piece of clockwork, dumb gears turning blindly in the dark.
Right.
But the modern quantum view sees the universe much more like a computer.
So, a universe processing its own information.
Exactly. Every time a particle collides, every time a gravitational wave stretches a cloud of gas, every time a photon is absorbed by a dust grain, well, the universe is physically computing its own state.
That is mind-blowing.
Every cause and effect is a mechanism of record keeping. The universe doesn't require an external conscious auditor to verify its ledgers. It's keeping its own books through the ceaseless interactions of its fundamental parts.
So what does this all mean? When we synthesize this entire journey, the web of everything concept beautifully marries the two conflicting perspectives together.
It really does.
It honors von Neumann's mathematical obsession with deep, interconnected logical structures. The universe isn't just random stuff, it's a dynamic, actively updating mathematical object.
Yeah.
But it also fully satisfies the mainstream physicists' reliance on decoherence. The universe calculates itself into solid existence, interaction by interaction.
It provides an incredibly elegant resolution. It removes the arrogant need for human exceptionalism, the mystical idea that primate brains possess some unique, reality-collapsing superpower.
Right, which was always a sticking point.
But it still acknowledges that observation, when defined broadly as physical interaction, truly is the fundamental engine generating reality.
Let's summarize where we've landed on this journey for you. We opened with a clear mission: does the universe need a witness?
And we uncovered two deeply compelling, historically significant perspectives.
Right.
The mainstream physicist argues that no external witness is required. The universe witnesses itself continuously through an infinite web of physical interactions.
That decoherence process.
Exactly. Decoherence is a mechanical process that weaves our solid, classical reality out of underlying quantum probability.
Meanwhile, the philosopher and brilliant scientific pioneers like John von Neumann look deeply at the underlying math and argue that physical existence and conscious experience might be too deeply intertwined to separate so easily.
True.
The exact boundary where physical quantum machinery ends and the subjective knowing of a mind begins remains one of the greatest blind spots in human knowledge.
It really does. And this debate serves as a brilliant reminder that theoretical physics and philosophy are not opposing forces.
No, not at all.
They are simply different tools utilized to excavate the exact same fundamental mysteries of existence.
Taking the time to think carefully about these concepts, about what it actually means to exist as a physical object or a conscious mind, is not a purely academic endeavor.
Definitely not.
It is quite literally one of the oldest, most important questions human beings have ever asked. Validating that deep-seated curiosity is exactly why we embark on these deep dives.
And if exploring the architecture of reality has sparked your curiosity, the source material provides some incredible resources for your reading list.
Oh, yes.
Carlo Rovelli's books on quantum mechanics and the nature of time are phenomenal. He manages to maintain absolute scientific rigor while writing with the insight and soul of a poet.
Strongly second that recommendation. And for the history buffs eager to learn more about the human computer himself, Ananyo Bhattacharya's biography of von Neumann, The Man from the Future, is essential reading.
It's a great book.
It really is. And if you are looking for something a bit more intense, Benjamin Labatute's book, The Maniac, offers a brilliant, somewhat haunting meditation on the absolute limits of pure rationality.
Before we conclude, there's one final, deeply unsettling puzzle hidden within all of this math and philosophy, something we haven't quite resolved yet.
Oh, the ultimate lingering mystery.
Exactly. Even if we fully accept the mainstream physicist's view, even if we completely agree that the universe simply witnesses itself through trillions of tiny, self-contained quantum measurements and atomic collisions,
Right.
why do those specific interactions produce a universe filled with consistent, stable, classical objects at all?
That is the big question. Why don't those trillions of random quantum collisions just result in a chaotic, formless soup of radiation?
Right.
Why do they reliably, consistently organize themselves into complex structures that make logical sense? Why do these blind interactions inevitably build grains of sand, distant fiery stars, and ultimately us?
The underlying mathematics of decoherence explains how the wave function collapses into reality, but it does not intuitively explain why the resulting collapsed state looks like a beautifully coherent, highly structured universe.
Wow.
It's a profound mystery sitting right at the bleeding edge of our current understanding of physics.
That is a thought to mull over the next time you look up at the stars or the next time you look at a mountain. We talked about a mountain at the very beginning of this deep dive.
We did.
The mountain that feels so permanent, heavy, and solid. You walk away, you close your eyes, and the mountain is undeniably still there.
Unchanged.
But it isn't there because it is a dead, static piece of rock waiting for a witness. It remains there because every single atom inside it is furiously, continuously witnessing all the other atoms.
Beautifully said.
The mountain doesn't need you to look at it because the mountain is already looking at itself.